Okay, great. So our final talk for the day is by Anna Romanov, who got up very early in Sydney to valiantly speak to us about categorification of the Lustig Vogan module.
Thank you, Ben. And good morning, everyone. I know that you're winding down in most of your days, but it's 6 a.m. here in Sydney, Australia, so my day is just starting. And thank you to the organizers for the invitation to give this talk. It's really great to be here across the ocean and getting the opportunity to speak to all of you. So I'm really happy to be here. I should see the chat. So today what I want to talk about is a categorification of the Lustig-Vogan module, which is a certain object that captures combinatorial data about a class of representations of a real Lie group. And, let's see. And so here's my plan. I'll start by setting the scene a little bit. So I'll tell you about the mathematical world in which this talk lives. And this is the world of unitary representation theory of real reductive Lie groups. And then I'll go on to define what the Lustig-Vogan module is. And this is going to be a certain module over the Hecke algebra, which tells us information about characters of irreducible, admissible GK modules. And then to complete this definition, I'm going to need to introduce a certain geometric category of equivariant sheaves, which controls the structure of this Lustig-Vogan module. And then I want to tell you about some work that I've been doing, providing an algebraic version of this category in terms of Soergel bimodules. And then finally, I'll put it all together and tell you why I care about this and why I think it's interesting and what I've been working on. And I will. So the main character for today's talk is going to be a real reductive Lie group. For example, you can think about SL2R, SON, UPQ, or my favorite example of today is going to be SP22. Normally when I give talks, I like to use SL2 as a running example, but today I decided to bump it up a notch and do this symplectic example throughout because it displays this story really beautifully. So keep this example in your head and it'll keep showing up throughout the talk. And the big guiding philosophy underneath everything that I'm going to be saying today is the idea that we want to understand this object, we want to understand a real reductive Lie group by studying its unitary representation theory. That is, we want to look at Hilbert spaces which admit an action of this Lie group by unitary operators. And this is a very old problem. People have been thinking about this since the 1940s. And in the 1950s, Harshchandra took this problem, which at first glance is an analytic problem. It's about Hilbert spaces, so harmonic analysis should be showing up, and recast the problem entirely in terms of algebra. And so the way that he did this is for any representation of a Lie group, we can obtain from it two other representations of related objects that are easier to study. So on one hand, we can take our representation and we can differentiate on the smooth vectors and obtain a representation of the corresponding Lie algebra, which we can then complexify. Or we can take the representation and restrict it to a representation of a maximal compact subgroup, and then we obtain a representation of a compact Lie group. So from a representation, we can get these two simpler settings, which are representation theory of complex Lie algebras and representation theory of compact Lie groups. And what Harshchandra realized is that we can completely translate our problem into these two other settings. And very roughly, the reason why this works, at first it seems like it shouldn't work, that these two processes are losing information about the representation we care about. But actually, it does work because the Lie algebra captures infinitesimal information about the group, but it loses all the information that distinguishes the group from any of its coverings. But then the maximal compact captures fundamental group information about the group we care about because it deformation retracts onto its maximal compact subgroup. So it exactly makes up for what the Lie algebra loses. So by keeping track of these two pieces of information, we can translate our questions about unitary representations to questions about GK modules. And this process that I've described doesn't have anything to do with unitarity so far. We could do this with any representation of our real Lie group. But it turns out that if we start with a unitary representation, the corresponding GK module we get has a nice property. And that property is that when we consider it as a representation of the maximal compact subgroup, it decomposes into irreducible representations because it's a compact Lie group. But each of these irreducible representations only shows up finitely many times as finite multiplicity, and this is a property that we call admissibility. And this motivates the general setting which I'll be working in today, which is the following. We'll start with a connective reductive Lie group, and within it we'll fix a maximal compact subgroup. And then we'll denote by G and K without the subscripts the complexifications of these groups. These have the structure of complex algebraic groups. And then we'll let the math frac letters denote their complexified Lie algebras. So in our favorite example of SP22, this means we're going to translate everything in terms of the Lie algebra, the complex Lie algebra SP4C, and the complex algebraic group SL2C cross SL2C, which is living inside of SP4 in this following way. Now, the representations that I'll be talking about today are the following. I'm interested in admissible GK modules, which are going to be a vector space that is simultaneously a finitely generated representation of the universal enveloping algebra, and also an algebraic representation of K, with the property that if we differentiate the action of K, it agrees with the action of the Lie algebra K that comes from the universal enveloping algebra action. And then also that as a representation of K, this thing should decompose into irreducibles and each should occur with finite multiplicity. Okay, so the point of those last two slides was that if we're interested in unitary representation theory of a real reductive group, this naturally leads to the study of admissible GK modules. So we can start by understanding these. And they have a nice classification in terms of geometry. So if we fix a Borel in our group, then we can look at the flag variety, which I'll identify with G mod B. And the group K acts on the flag variety with finitely many orbits. And then the collection of irreducible admissible GK modules with some fixed infinitesimal character is parameterized by the collection of irreducible K equivariant local systems on those K orbits. And this parameterization can be realized explicitly if we use Balance and Bernstein localization. So Balance and Bernstein localization gives us an equivalence of categories between a category of admissible GK modules with a fixed infinitesimal character. These are sometimes called Harish-Chandra modules, and a collection of K equivariant D modules on the corresponding flag variety. And then on the geometric side, we can realize all the irreducible objects in the right-hand category by taking irreducible K equivariant connections on orbits, pushing them forward using the D module functors, and then taking the intermediate extension. And this classifies all simple objects in this Harish-Chandra sheaf category. And then we can take global sections of this whole story, and this gives us two collections of modules, of GK modules. One collection of standard modules, which I'll denote with M's, and then all irreducible admissible GK modules with this fixed infinitesimal character show up as quotients of these standard modules. So let's see this in example. So in the SP22 example, we can describe the geometry of these orbits really explicitly, which is why I chose this example. So the flag variety in here is going to be the symplectic flag variety, which is the collection of flags in C4, which satisfies some extra conditions depending on the symplectic form. So a point in this flag variety is going to be a flag, which is an isotropic line in an isotropic plane, and the complement of the line in C4. And this is small enough that we can, this is really just a choice, or this is a point in the flag variety is two choices. It's a choice of an isotropic plane, and then a choice of a line within that plane, which is automatically isotropic. And so by projectivizing, we can draw a picture of this, which is why I like this example. So we can draw our isotropic plane as a line in P3, and we can draw our line as a point in P3. So I'll draw points on the flag variety by this little caricature over here. And then what I want to do is I want to look at what the orbit structure looks like if we act by this group K. So K acts on these flags just by matrix multiplication. And there are two subspaces that are stabilized under this action. And these I'll draw as two non-intersecting lines in P3. And then to see what the orbits look like, we can think about how a generic point in our flag variety interacts with these two subspaces. So we have four options. The most generic case is that our line, which I'm calling P, doesn't intersect at all with these stabilized subspaces. And this is going to be the open orbit of K, and this will be a four-dimensional space. And then we have three other options. Because we're imposing this isotropic condition on our line, these aren't just any lines, they're isotropic lines, we only have three other ways that they could possibly intersect with these stabilized spaces. And so if they intersect with P1, they have to intersect with P2 as well. You can write down the conditions on the symplectic form and see that this is true. And so the second most degenerate case is what we get if both of the both P1 and P2 intersect our line. And then we have two closed orbits corresponding to the case where the line or the point is actually on P1 or P2. And now if you think about these closed orbits for a minute, each of these is going to look like a copy of P1 cross P1. We have a P1's worth of choices for where the point lies on either P1 or P2. And then we also have a P1's worth of choices for where the line could possibly intersect the other one. And this is reflecting the fact P1 cross P1 is exactly the flag variety of this group K. So the closed orbits here, we have two closed orbits and each of them looks like a copy of the flag variety of K. And then you can check that if you take any point in this flag variety and look at the stabilizer in K, it's going to be connected. And this tells us that the only K equivariant local systems are trivial. And remember that the point of this is I'm trying to tell you something about irreducible admissible GK modules. So we have four orbits and only trivial K equivariant local systems. So we can conclude that there are exactly four irreducible admissible GK modules in this example of some infinitesimal character. Oh, I suppose I could look at the chat while I'm going. Oh. Which line is the point on? Oh, maybe I should let other people talk that out. And I will continue. But we can come back to this maybe at the end of the talk, and I can show the slide again later. So far, I've set some scene where I have a category that I care about, this category of admissible GK modules with some fixed infinitesimal character. And this is a finite length abelian category, and its simple objects are classified as quotients of certain standard objects. So in this setting, it's natural to ask about multiplicities. So in other words, in the growth and decay group of this category, if I express the standard objects in terms of simple objects, what are these multiplicities? And the answer to this question is given by the Lustig-Vogan module in the title of my talk. So now I'll tell you what this is. So from this data, we have an associated Coxeter system, which is just the Weyl group of G. And within this Weyl group, we have a reflection subgroup, which is determined by the Weyl group of K. And we also have an associated Hecke algebra, which for me will be an associative ZVV inverse algebra with generators given by simple reflections satisfying these two relations. And this Hecke algebra has two bases, has the standard bases, and it also has a Kazhdan-Lusztig basis, which I'll denote by B's. So in our example, the root system of SP22 is type C2. So our root system is generated by alpha and beta in this picture over here. And the Weyl group has this form that I've written down. And the reflection subgroup that we get from K is the subgroup generated by reflection through the hyperplane orthogonal to alpha and reflection through the hyperplane orthogonal to 2 beta plus alpha, which are the two that I've highlighted here. And so this is a reflection subgroup, but it's not parabolic. So it's not generated by simple reflections, but it is generated by reflections. And it looks like Z2 cross Z2. Now, what I'm trying to do is I'm trying to build some sort of module that captures information about this multiplicity question that I introduced a few slides ago. And the idea for how to construct this is to imitate the classical story in Kazhdan-Lusztig theory. So we're going to try to construct a module for the Hecke algebra. And the starting place is we want it to have some basis that's parameterized by the simple objects. And this is going to correspond to the Weyl group. So this will be the collection I told you earlier of pairs of a K orbit on G mod B and a K equivariant local system on that orbit. And then the next ingredient we need is a length function. And so in the classical setting, we have length in the vial group, which is the same as dimension of the corresponding Bruhat cell. So in this setting, we can take our length function on our parameterizing set to just be dimension of the corresponding orbit. And then we'll let MLV be the free ZVV inverse module with a basis given by this set. And this is just going to correspond to the Hecke algebra, which at first glance is a free ZVV inverse module with a basis parameterized by the vial group. And then we're going to give this the structure of a right H module, which will correspond to the right regular representation of the Hecke algebra. And I'll put this as a bit of a black box for now, and I'll tell you exactly what this action is in a few slides. And then the last two ingredients we need for Kazhdan-Lusztig theory are some partial order, which would play the role of the Bruhat order, and an involution, which will play the role of the Kazhdan-Lusztig involution. And these two things can be constructed, but I don't have time to go over them in detail. So for now, I'll leave these as a bit of a black box too. There is a partial order on G, and there is an involution satisfying appropriate properties on MLV. And then with all this data, the big theorem of Lustig and Vogan was that for every element in our parameterizing set, we can find some unique self-dual element in this module, so that the relationship between these two things is given by a collection of polynomials, which satisfy some properties, and these are the Kazhdan-Lusztig-Vogan polynomials. And then the punchline is that these polynomials exactly determine the multiplicities that we were asking earlier. But as of now, you shouldn't be satisfied yet because I haven't actually told you how this module is a module over the Hecke algebra. And the reason for that is that I need to introduce some more geometry to describe this action. So the first thing I need is a categorical upgrade of the Hecke algebra. And we can find this within the B equivariant derived category. Now this is a monoidal category under convolution. Oh, this decomposition theorem should have gone lower. So this is not because of decomposition theorem. This will come in a second. But this category contains all of the B equivariant intersection cohomology sheaves with Schubert varieties. And so we can define a geometric Hecke category within here as the category generated by all of these IC sheaves under closed under direct sums and homological shifts. And this is also a monoidal category under convolution, and this is because of the decomposition theorem, so move that down a little bit. And this category gives us a geometric categorification of the Hecke algebra. It's a monoidal category, so if we take its growth in D group, then we get an algebra. And we can also give the growth in D group the structure of a ZVV inverse algebra by asking that V act by homological shift. And then this thing gives us, so then the growth in D group is actually isomorphic to the Hecke algebra. So this is our first step. And then we want to play the same game for this Lustig-Vogan module. So we'll find a categorical upgrade here within the K equivariant derived category. And within this, we also have IC sheaves, which will be, which in this case will be what we get if we take a K equivariant local system on one of these orbits and take the corresponding intermediate extension and shift by dimension. And now convolution gives us a right action of this geometric Hecke category on here. And we can define a geometric Lustig-Vogan category by taking all of the IC sheaves corresponding to closed orbits and then convolving with the Hecke category. And this is going to play the role that we'd like. So if we take the split growth into group of this category, again, we can give it the structure of a ZVV inverse module in the same way we did with the Hecke category. And now this is some module that has the correct basis. It has a basis that's parameterized by these IC sheaves. So they're exactly parameterized by our set D. And so we can identify it with MLV just as ZVV inverse modules. And now if we take stock of what we've done so far, the convolution formalism gives us an action of the geometric Hecke category on this geometric Lustig-Vogan category. And so that means that the split growth in D group also has the structure of an H module. So finally, this is the action that defines this Lustig-Vogan module. The way that a Kazhdan-Lusztig basis element acts on some class of something in the derived category is the same as as convolving with the corresponding IC sheaf. Now, all of this can be reformulated algebraically in terms of the language of Soergel bimodules. So for the rest of the talk, we'll assume that the group is equal rank. So in other words, I'm just doing this so I can assume that G and K share a maximal torus. And then I'll let T be the Lie algebra of the group T. And I have two rings corresponding to this picture. The first is just the symmetric algebra on T star. And this has a natural action of the Weil group, so it has a natural action of the reflection subgroup corresponding to K. And I'll let RK be the invariance under WK. So in our little example, R is just a polynomial ring in two variables, and RK is the invariance under this group. And now I can define a special class of RR bimodules corresponding to every expression of an element in the Weil group. And these are Bott-Samuelson bimodules, and they're written down in this following way. And these are the building blocks of the category of Soergel bimodules. So if we take the category generated by these, we end up with another category which categorifies the Hecke algebra. This category can be given the structure of a ZV inverse module by asking that V act by grading shift, and then its growth in D group is an algebraic categorification of the Hecke algebra. So we can try to play the same game using the pieces that we have so far of the Lustig-Vogan category. We can construct an algebraic version as follows. So our first step is that we want some collection of generating objects. And these we're going to build from minimal coset representatives in the quotient of this Weil group by the reflection subgroup. So for every one of these minimal coset representatives, we can build an RKR bimodule by just taking R as a vector space and then giving it a left RK action just by left multiplication and a right R action, which is twisted by our chosen element of the Weil group. And these are so-called standard bimodules. And then from these, we can define a category by tensoring with all of the Bott-Samuelsons. And this category is now going to have a natural action of Soergel bimodules because its objects are RKR bimodules. So we can always take the tensor product on the right over R with anything and it's a Soergel bimodule. And it has, so this tells us that its growth in D group has the structure of a right module for the Hecke algebra. And just a quick remark about these guys is this construction has nothing to do with the fact that our reflection subgroup came from a real Lie group. We could do this for any reflection subgroup of a Coxeter group. And in general, these categories are not very well understood. For example, it's not known if they have finitely many indecomposable objects or if their growth in D groups can be described combinatorially in some way. And now let me put it all together because I don't have 2 minutes left. So what have we done so far? This has been a bit of a lightning journey. But so far what we've done is I've told you that there's some module for the Hecke algebra, which tells us something about the character theory of an irreducible admissible representations of a real Lie group. This was MLV. And the way that this thing was defined was as the growth in D group of a geometric category. And then I defined some algebraic category whose growth in D group also has the structure of an H module. And so the hope is that this algebraic category also provides a categorification of the Lustig-Vogan module in a different language. And the reason why this is the hope is, here's a few reasons why this might be interesting. One is that this could provide a setting for an algebraic proof that the Kazhdan-Lusztig-Vogan polynomials describe characters of irreducible admissible representations. And also, going back to what I had mentioned a few slides ago, from a Soergel bimodule perspective, it gives a geometric description of an interesting class of module categories over SBIM. And in particular, if we know that these categories come from real Lie groups, then we know that their indecomposables are given by this parametrizing set I told you earlier. So in particular, there's finitely many of them. And this tells us something, it gives us a geometric description of what the category looks like. And then it gives us access to more tools in the study of real Lie groups, the tools of Soergel bimodules. And then finally, it could potentially provide an algebraic setting for a conjecture of Soergel on Vogan character duality. Now, putting this all together, there's a way that we can go from this geometric version of the Lustig-Vogan category to the algebraic version, and this is equivariant hypercohomology. So we have a functor in one direction, and this functor intertwines the geometric Hecke algebra action, or Hecke category action with the Soergel bimodule action, and it sends generating objects to generating objects. The IC sheaves get sent to these standard bimodules that I defined. And so if we could show that this functor is fully faithful, then this would provide an equivalence, and then this would show that this Lustig-Vogan category is an algebraic categorification of the Lustig-Vogan module. And finally, just a remark that this story is a special case of related work by Bezrikov-Nikov-Volonin in their paper Causal Duality for Quasi-Split Real Groups, in which a categorified Lustig-Vogan module provides a combinatorial setting for a proof of Soergel's conjecture in a special case. And yeah, that's the end of my time. So I will end here. I ignored everybody's questions because somehow I haven't figured out this technology of Zoom talks yet, and reading the questions while talking is too much. So maybe I'll read them now. Also, you can ask them out loud.
I mean, I think only the last one by Stephen really needs to be addressed at this point.
So everybody, so if I ignore the questions, other people take care of them. That's convenient. For reflection subgroups that are parabolic, is it better understood? Oh, you mean this category? I also don't think it's understood in that case either. In general, there's been more work done if you have a parabolic subgroup about these categories of types of bimodules that look like RKR bimodules, but these specific categories, I don't think that there's much more known about them, even if your reflection subgroup is parabolic.
Can I ask a question? So, well, in our paper with Kari Volonin, well, as you do, we consider the global cohomology functor for the principal block. So, I mean, so this all dilated setting, and so on one side we have quasi-split group, and on the other side we have an arbitrary group and principal block, and then it makes sense to consider the hypercohomology functor. And what remains a mystery for us, I guess, is would be a good generalization of that to other blocks. I mean, so where hypercohomology functor just vanishes. So does your method suggest anything?
I don't think so, unfortunately. I'm also not sure.
We're considering various possible generalizations, and maybe one of them will.
Yeah.
At some point we decided one of them is a good one, but we still haven't.
Yeah, the problem with this method too is that it's relatively restrictive in terms of the classes of groups that it applies to.
So you've been only considering principal block, right?
Yes, yes, I have.
I have a basic question, which is, is it somehow straightforward to compute, say, what the k-type of one of these standard modules is?
Say what the k-type of, I'm not sure. What do you mean by straightforward to compute?
Basically the things corresponding to Schriek extensions. So if you know the change of basis between them and simples, basically, how does that, normally for category O, that'll tell you, like, say, the characters of the simples. And I guess
Oh, I see.
Yeah.
So I phrased this as a multiplicity question between standards and simples, and then sort of claimed later that this is telling us about characters of simples. Is this what you were?
Sure.
I'm sorry.
Yeah.
I think I don't quite understand your question.
It's, I can ask you later. It's not a big deal. Yeah. Thanks.
I wish I could see. Somehow I still haven't figured out Zoom, and I can't actually see who's talking either.
Well, if they don't have their video on, then you can't see them.
Well, I assumed that at least their box would pop up with their name, but it's not.
Yeah, Roman and Gerbier's boxes have popped up, but they just say Bezrukov and Gerbier for me. So
We only have hide video participants without video checked.
oh yeah,
Oh, okay. So now I can see Ben.
Roman was video was open.
oh yeah. I guess it was while he was asking the question, but then he disappeared.
Is it? Doesn't Vogan have a lot of papers about what Gerbier was asking about?
Oh, yes, I think so, but I think I just didn't quite understand the question. But yes, there's a series of papers, 1 through 4, irreducible characters that exactly describe this story. So.
Okay, great. Thanks. Let's take a look at this. That's awesome. Yeah.
I would be very curious, sort of, to which extent there's evidence for this fully faithfulness in this context. I mean, say SL2R, for example, would be an example, or sort of.
Well, the problem is SL2R is not equal rank, so it doesn't satisfy the condition I've imposed. But I think that it is very likely that this functor is going to be fully faithful. I mean, in particular, because this work of Roman and Belonen, this is a special case of that. It's phrased in slightly different language, but they have a proof that equivariant cohomology is fully faithful in their setting.
Mm-hmm.
Yes. There's some.
What if your running example, the SB22 example?
What's that?
I mean, SL2R doesn't work because it's not equal rank, but isn't SB22 equal rank?
Yeah.
So does it work in that case?
But sorry, if I may comment. So in our theorem, we do not assume equal rank. So we just take principal block. Maybe if you literally want to take homology, maybe there is some assumption like it should be maybe simply connected or adjoint or one of those things. But you can extend the easy to slightly modifying the statement. One can extend it to any principal block in any real group.
But in the SB22 example, it is fully faithful.
Okay, cool.
When I read about the Lustig Vogan module, I read about it in terms of involutions or twisted involutions. And is that the same thing? Is that the involutions in bijection with D?
Some twisted involutions.
Or am I thinking about a different Lustig Vogan module?
I think there is a different.
Yeah, I'm not familiar with this. The version of it that I've read about in the Vogan papers and in this K orbits on flag varieties paper, Lustig Vogan is in a similar formulation to the one that I gave. But maybe.
So are there really two different Lustig Vogan modules with different Lustig Vogan polynomials? That would drive me nuts.
That seems strange.
Remember, it's Kazhdan-Lusztig Vogan polynomials.
Which might be different than Lustig Vogan.
Yeah, well, I mean, somebody should have told Lustig to ease off at some point, but. I mean, I guess a sort of related question of the full faithfulness is sort of what's the kind of obstruction to proving it, right? There, like, do you have to prove some cohomology vanishing or like?
Yes, you need some cohomology vanishing, but I think that this is established already in the work of Vogan. So hopefully the obstruction is just time.
It'd be hard to find right now.
But right now it seems, at this stage, it doesn't seem like there are any great obstructions, but we will see.
Elijah has just informed me that this involution thing that I'm thinking about is a special case. Or it's probably a special case when G is G times G and K is G. Although that's not compact, so it's probably not a special case, but something similar.
No, but
No? Okay, good.
it doesn't look like.
He was just guessing, so.
Seems plausible, right? That's a pretty important special case.
Yeah, but
Well, I would love it if it works this way, yeah.
Well, maybe Elijah made an amazing discovery.
Yeah, sorry.
So I have one last question, which is, I mean, have you thought at all about replacing B with P?
No, why?
No? It's a good thing to do sometimes. But yeah, I don't know. Does that have any interesting interpretation in terms of real groups?
I don't know. Yeah, I'm not sure.
Okay, I absolutely agree. Yeah, this would be very interesting and natural.
Wait, I mean, it would be very interesting because it says something about real groups, or just like, you know, it's always cool to use more general parabolics.
No, I mean, it because sort of on the causal dual side, replacing E by P would correspond to considering singular blocks.
Mm-hmm.
So yes, it would be very, very natural, and to have a similar sort of fully faithfulness thing. I would very much expect that to be true, and it would be really wonderful to have sort of this kind of coherent picture for real reductive groups, because it's mostly missing.
All right, you had a request to show again the definition of MLV.
Why? Let's see. I assume you mean the green one.
You know, whichever color you think is best.
Well, the red one's the geometric one, so I don't think that Leo wants to see that.
So, sorry, you make this comment that it's rather mysterious. And do you know in any reasonable cases, like how many indecomposable objects there are in this category?
No. So I guess that's why they're mysterious. Well, in any case, if this is an algebraic categorification, then we know in this collection of cases that come from real Lie groups. But outside of that, I don't think that they've been particularly studied.
But yeah, it's sort of a funny thing to do.
Ben's shaking his head. He's one of the four.
I'm just looking up this Lustig-Vogan involution paper and seeing if it says anything about the other Lustig-Vogan polynomial.
So sorry, I missed. So the Lustig-Vogan module itself, does it have a description in terms of like generators and relations for the Hecke algebra, or do you only have these kind of categorical descriptions of it?
It just has this geometric description.
Right.
And it can be kind of formulated in a few ways, but it comes down to geometry.
So there's not a description just purely in terms of Hecke algebra or something?
No, I don't think so.
So what I can share my probably incomplete understanding of this. There is a sorry, is it me? So there are different k orbits. So to a k orbit on Gmod B, you can attach a conjugate class of Cartans. And if you fix that, somehow this, if you can group the orbits together according to this, and this doesn't give a direct sum decomposition of this Hecke algebra model, but it gives a filtration. And the associated gradient of this filtration maybe has some description like Sam wanted. So it's some basically deformation of some permutation module of the wild group. Something like that. But yes, so the whole module maybe doesn't have a natural description. So that's my picture, but I mean, I don't know, maybe Wolfgang can correct me or add to this, but I don't know.
So I mean, can just
Yeah,
like
I mean,
So let's try to the cross-section that Vogan defines on the set of irreducibles, which...
yeah. Yeah, I mean, the combinatorics is just complicated, but still sort of explicit.
Yeah, that's what I was going to ask. So like, I mean, in a group case, it's purely like finite dimensional linear algebra. Like in principle, a computer can find Kazhdan-Lusztig polynomials, but is it true for these Kazhdan-Lusztig Vogan ones also?
Yeah, they can all be computed using Atlas. So they...
A calculation big as Manhattan. I mean, this is which puts us on the same level as the Human Genome Project.
Yes, right.
In the Atlas project, they do it all, yeah.
But is it? I mean, like, if you can't write down a basis for the module canonically or something with its action, why is it even in principle?
No, I mean,
Oh, you can. It's all programmed on the computer, yeah?
Well, I know computers can invert matrices painfully, but I don't see, but if it's not given by, if this Lustig Vogan module isn't given with some favored basis, well.
no, it has canonical basis, yes. And
but I mean, how do you,
I mean, I think Sam is asking, is there some reasonable indexing for that canonical basis?
yes, I think so, yes.
Yes, I think so too.
Because they have programmed it into Atlas, so it has a combinatorial description that a computer has been able to understand.
Okay, Sam, I think that's called proof by intimidation.
yeah. Well, the indexing is by the set D, but it's in two different, and the ways have to do with like the action of.
Yeah, but I think it has some indexing involving things like order 2 elements, involutions on Cartan and things like that. So
That sounds like it does have a purely Hecke algebra style description.
That also sounded like Ben Elias's cue to come back and be like, I knew it was involutions.
Yeah, right.
You said it.
Moment.
Or maybe he already left.
Mm.
Yeah, I think he's off the call. So sorry, what would you change to think about the other blocks? Roman, you were sort of saying, making this point about the principal block versus other blocks.
right, I mean, Vogan's method for other blocks doesn't work at least as literally in that So on the dual side, so on the dual side we have a quasi-split group, and then the dual to taking the global cohomology has to do, for example, with translation to the most singular central character. And for the groups which are not quasi-split, just there is no, the translation vanishes. And so dually, well, the global cohomology functor also vanishes for obvious reason, because global cohomology is just X from the constant sheaf.
Sure.
And so if you have some block which doesn't contain a constant sheaf, then X certainly has to vanish. So there should be some replacement for that in the game. Maybe there is, but just, maybe there is one, but just one needs to find it.
But I mean, you still have, I mean, it's still in this framework of D-modules on the flag variety, right?
Yeah, no, it's just a different block.
Yeah, and you still have the Hecke action, all that good stuff.
No, yeah, all this is available.
Yeah, it's true. If you think too much about category O, it kind of lulls you into a false sense of security about this stuff.